Even during his last days, Albert Einstein was frantically searching to reconcile quantum mechanics with general theory of relativity. The current challenge of physics as well as mathematics lies in reconciling the very big general theory of relativity with the quantum realm, which is very small. And definitely on the progress of scientific research and advancement, string theory is something which gives a promising future. At least as far as mathematics and physics is concerned, as far as the evolvement of scientific models are concerned, string theory seems to get a possible answer, unification of the very big with the very small. In this particular video of string theory, I am going to give you a complete tour on understanding string theory, why it evolved, what are the necessary components, what are the fundamental components, what are the fundamental concepts, as well as a brief and a very interesting history in understanding string theory. String theory is one of the candidate theories of quantum gravity, and it is the current scientific research which is looking forward to find an answer in order to find what we call is a theory of everything. So you can just sit back, take a pen and a paper and note down all those things which are very important in understanding string theory. This is one complete video which is going to give you all the fundamental components, understanding, researches, and what is very important in understanding today's progress in science. My name is Shaunak and you're watching this video on my channel Physics for Students. Season's greetings and a warm welcome to watch this video. First, let us understand what is string theory. Now, typically in traditional particle physics, we used to identify particles as what we call point-like particles. Now, we will definitely see the reason, but these point-like particles, you can just visualize them as dots, 1, 2, 3 points, are now being visualized or being hypothesized into something which is called a one-dimensional string. Just like a thread or a ribbon to make a visualization better, these point-like particles are now kind of a one-dimensional string which keeps on floating through space and time. These strings at a certain point, they interact with each other, producing what we call fundamental interaction at the quantum realm or at the quantum level. So on distance scales larger than the string, it looks like ordinary particles which has got a mass and a charge and other properties which are determined by its vibrational state. Now, because string theory is all related to strings, you can imagine that when you are striking the chords of a guitar, it is all about vibration. And out of these vibration, different particles, emission, etc. are produced, and one such vibrations, physicists are looking what we call is a search for graviton, or the fundamental hypothetical particle which once we found can definitely clear up the house of the standard model. So let us find out a simple and a clear definition of a string theory. Right on your screen you will see I have just given, it is an attempt to unite the two pillars of 20th century quantum mechanics with Albert Einstein's relativity. Now, the name string theory, as you can see on the screen, comes from the modeling of subatomic particles, which are tiny one-dimensional string-like entities. So the most popular candidate theory, now I have spoken to this in my previous video, but just to tell you, these are called candidate theories. So quantum gravity, being basically the subject, has got different theories, like theories related to quantum gravity, for example, string theory. Then there are other theories which is called loop quantum gravity. There are several other theories, but among those theories, what seems to be very promising is called the string theory. So it is the most popular candidate theory of gravity which attempts to reconcile the very big general relativity with the very small quantum mechanics. The basic reason, as you understand, is that once we reconcile with the very big with the very small, then what we get is called a TOE, or a theory of everything. Definitely, isn't it a wonderful idea to unify everything, and instead of going from here to there, we get one particular theory which will speak out everything. You're right, it has not yet been experimentally proved. Neither we can find out those weird, approximations which string theory gives. But as you know that in the during the journey of human civilization, it is all hypothesis, it is all probabilities. But through the one day we find a complete proof, and then from hypothesis it becomes a scientific truth. So this is what is called a basic idea and definition of string theory. We won't be looking towards point-like particles, but we have to imagine them as wiggling and swiggling, beautiful ribbon-like structures, or strings which moves and vibrates among the area of space and time. We all know there is a famous saying which is called necessity is the mother of invention, and it is this necessity which brought about string theory. What is that necessity? Why do we need at all a string theory? Let us find it out in the next part of our video. Well, with the advent of Isaac Newton's Principia Mathematica, well, I consider to be one of the revolutionary work ever done in the history of science. The scientific world now really knows that how the force, momentum and everything behaves. Newton's Principia Mathematica taught us and gave us a complete solid foundation on the mathematical formulations of force, momentum, inertia and everything. From Newton's Principia Mathematica, even further when he predicted the laws of planetary motion, how things orbit around a specific gravitational force, we enter into what is called the classical world of physics. Now, just note that I recently this particular point, what do we mean by classical physics? In general, when we talk of classical physics, you will see that classical physics, generally people try to understand what is not modern. So the mathematics is classical, the ideas are classical. No, I'm not talking of that. Classical physics in this string theory context actually means that something which is deterministic, something which is quite calculatable, or we can calculate them based on certain initial conditions. For example, we all know a ball, or if you throw a ball right on the wall, then it will come back, and we can really tell that this is the position which is going to come back. This is the location where it is going to land. So if I take, for example, a very simple example, a coin, and you can just imagine that the coin is glued on the table, then what is the classical determinism which predicts the future? For example, if the coin is facing only the heads, then it will be head, head, head and head. If it fails tail, then it will be tail, tail and tail. And now if we got two conditions, head and tail, then from head we go to tail, so it will be HT, 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 and we are coming from tail to head, it will be TH, TH and TH. That is what is called that given certain conditions can we reverse the system. However, I'm not talking of reversibility now, which is a part of thermodynamics you can look up in your textbook. Now, given with Newton's advent and further with, as we proceeded with the history of physics, we find that this world is really deterministic. We are happy. The laws of mechanics, the electricity, magnetism, everything was going quite well. Until and unless this gentleman appeared, Albert Einstein, who formulated the special theory of relativity in 1905, which actually gave a completely new way of looking at space and time. The forms of causality changes. There were certain, I would say, predictions of special theory of relativity. We got what is called a time dilation. We came to know the speed of light is constant in vacuum. The inertial frame of reference now moved into non-inertial frame of reference, Lorentz transformation, and a lot of things. So now you see that from classical mechanics, although relativity is still considered to be classical, we moved into somewhat we called a relativistic world. But the final blow came in 1915 when Albert Einstein published his magnum opus, Einstein's General Theory of Relativity. Right on your screen, I have given a very basic idea or a basic description of what is called a space-time curvature. With Einstein's relativity, general relativity, we now come to know that the force which was conceived by Isaac Newton as something fictitious is no more a force. It is just a space-time curvature. It is this space-time curvature which causes gravity. Technically, we call them geodesics, which led to the deflection of starlight, which ultimately let us know that it is the presence of mass which causes the space-time curvature. Huge change in the terms of physics, mathematics, philosophy, etc. Now we consider tensors, stress tensors, etc. So now we know that it is the presence of mass which causes a space-time curvature, and this curvature on the dent over the implications were many. Today we are talking and using satellite phones and tracking Ola and Uber over mobile. These are GPS system which ultimately came from Einstein general relativity. Black holes, wormholes, everything, a huge change in terms of physics and mathematics. So a person emerges with us, Werner Heisenberg. When we enter into a quantum realm, he gave us the entire world a new way of looking at the quantum mechanics. This is known as Heisenberg's uncertainty principle. I have just given a basic, very simple definition of Heisenberg's principle. Right on your screen, you can see the position and the velocity of an object cannot both be measured at the same time, even in theory. The very concept of exact position and exact velocity has no meaning in nature. Any attempt to measure precisely the velocity of a subatomic particle, such as an electron, knock out and in an unpredictable way, so that a simultaneous measurement of the position is no more possible, is not valid. So now you see that we enter a world which is called a quantum world, or a world of probability. That means at any point of time when you are trying to measure a particular subatomic particle, the more we try to measure precisely either the position and momentum, we are not being able to understand. So now you see this is called a quantum world. It's different from the relativistic world, because here we are dealing with chances. Here we are dealing with probability. So what I am trying to make sense is that when we enter into a probabilistic world, this world is full of probability. We cannot tell that if we fire a cannonball, or if we throw a ball, or if we move on a particular object, it is going to land up there. No. We can only say that there is a probability of 60, 40, 70, 30, or something that there might be no probability that we can find a particular subatomic particle or an electron over there. So this is a kind of a paradigm shift entirely from a classical world where everything was deterministic into a quantum world where nothing is deterministic, everything is probabilistic. Even with Heisenberg's uncertainty principle, when physicists try to find out something which is called a Big Bang, where the entire universe is condensed into an infinitesimal point, which is called a singularity, or even a black hole, there also quantum realm starts working. Right on the screen, I have given you a basic idea of how the black hole looks, and you see at singularity, when everything is confined to a very infinitesimal small point, the Heisenberg's uncertainty principle or the quantum mechanics comes into play. Now I will just show you that how it is different. Right on your screen, you see physical quantities are described by quantum state, which gives a probability distribution. If you try to measure one property, gives rise to a decreased specificity of the other. So what happens is that when if you have read Hawking's paradox or Hawking radiation, you will see that at black hole or singularity, when everything is confined to a very infinitesimal point, the quantum mechanics play, the quantum realms comes into play. So because black hole etc. is something which is related to general relativity, and quantum mechanics is something which takes place at a very quantum realm, herein lies the problem. We have to bring in general relativity in order to find out the very big, and we have to bring in quantum realm or quantum mechanics also in order to find out what is happening at those small points. And we find there is a big reconciliation. Einstein's general relativity doesn't work well at quantum realm. So the basic difference, right on your screen, you will see the nature of the gravitational interaction in particular, the equivalence of gravitational inertial mass, which represents gravity as a property of space-time rather than a field propagating in space-time background. This is where we call the biggest difference between quantum realm and the classical physics. Classical physics takes space-time geometry as something as a property of space-time, is an intrinsic geometry, whereas quantum physics takes something which is moving in the realm, or it is the background, there is a continuous field which is working. So that is what is string theory, because string theory is one of the candidates of quantum gravity. So now you see what was the necessity. The necessity is to reconcile gravity with quantum mechanics, because we have to find out what is going at singularity. We have to find out what is going at quantum realm. So that is what is called the need of string theory. Now that we understood that yes, we really need string theory, otherwise reconciliation of the big and the small is not possible, the question comes is that how at all string theory began. Who were the founders and how do we find string theory evolved through the time of physics and mathematical development? Coming up in the next part of your video. We must note that string theory is not a very old theory. So if you go back to internet or speak to your professors in order to find out a little bit more about string theory, you will see you are not starting something beyond 1935 and 40. And exactly it is so. So string theory is actually started, if I take the culmination route, it is around 1943 where Werner Heisenberg framed what is called S-matrix theory. S actually stands for scattering matrix. Just to tell you in brief is that S-matrix tried to replace quantum field theory and wanted to create a kind of a mathematical abstraction where space and time is being measured in terms of a mathematically abstraction, which is a kind of a matrix. So all those particles interaction would represent instead of a space-time matrix in a space-time dimension instead of a matrix. So there will be an infinite past and it will be an infinite future, and making that in a mathematical abstraction becomes easy for that. So that was basically the culmination of what is called string theory. The root of string theory was planted using S-matrix. Right on your screen you can find it out that it actually started with S-matrix theory, a research program by Werner Heisenberg. The theory presented a radical thinking of foundations of physical laws. By 1940s it became clear that the proton and the neutron were not point-like particles. 1959 you can see on the right hand side, Tullio Regge, a young theorist in Italy, discovered that bound states in quantum mechanics can be organized into families as Regge trajections. The first model in which hadronic particles essentially follow the Regge trajectories was the dual resonance model, later found out by Gabriele Veneziano around 1968, who noted that Euler beta function could be used to describe four-particle scattering. Later in 1969, the Chan pattern rules proposed by Jack E. Patton and Hong Mo Chan enabled isospin factors, which added further to the Veneziano model. So we completed something around 1969, and now we move up further into the history, and here you will find our dear professor, I won't tell, a very favorite professor coming into work. Right on your screen you can see in 1969 and 70 it was Yoshiro Nambu and Holger Nielsen and Professor Leonard Susskind presented a physical interpretation of the Veneziano amplitude by representing nuclear force as vibrating one-dimensional strings. However, this string-based description of the strong force made many predictions that directly contradicted experimental findings. So you see Leonard Susskind working along with Yoshiro Nambu and Nielsen made further advancement in string theory. We move to the next era, 1974. Quickly on your screen, you find John H. Schwartz and Joel Shirk independently with Tamiyaka Yonega developing something which is called boson-like pattern of string vibration, and found that their properties exactly match with those of graviton, which is the search for the hypothesized particle of gravity. And that is what they found, that the gravitational vibration the vibration of the string theory might match with something which we call graviton. Further, we move into 1984 and 1995. And now this is the time where something killed which is called the first superstring revolution, and it was realized that string theory was capable of describing all elementary particles as well as the interactions between them. Hundreds of physicists started working on that. The revolution was started by a discovery of anomaly cancellation in type 1 string theory via Michael Green and John H. Schwarz, which came to be known as Green-Schwarz mechanism roundabout in 1984. So we take a pause right now in 1984, and what we find is Green-Schwarz mechanism. Now, however, here one thing becomes very important. Two concepts emerge during this process. One is called a superstring theory, another is called a supersymmetry. Now, superstring theory is basically again a theory, an attempt to unite all the fundamental particles together and to find them as vibrations in certain supersymmetric strings. This is what is called superstring theory, whereas supersymmetry is a kind of a space-time symmetry between two basic particles. One are called bosons, which follow what is called Bose-Einstein statistics, and another is called fermion, which follows the Fermi-Dirac statistics. If you are looking a little bit more to know about that, I have given this link on the I button. You can click to my previous video. So now what happens is that with superstring theory and supersymmetry coming, one concept emerges. Right on your screen you see we need a theory which would unite a boson and a fermion, because the old string theories only consisted of bosons, which resulted into 26 dimensions. So you see, we came across the entire history of superstring theory. The initial was bosonic string theory, which resulted into 26 dimensions and did not consider fermion to take into account. And later, the physicists took into account fermion, which resulted into superstring and supertheory. Now, during 1985, 5 important string theories emerged. You can see on your screen. Type 1, Type 2A, Type 2B, SO32 and E88. I'm not going to explain this because it has been explained in my previous video. You can have a look. Further, we move into the era of 1994 and 2003. You can see Edward Witten, who created 11-dimensional M theory, and Joseph Polinsky, and discovered the need for a higher dimensional objects with D branes, and Juan Maladikena discovered what is called ADS-CFT correspondence, that is anti-de Sitter space. Now, M theory is something which we are going to look definitely, and D branes also we are going to look, but ADS-CFT is a very, very important discovery. It is a little bit more heavy and technical, so I'm skipping ADS-CFT into this part of the video. This completes what is called a brief history evolvement process of string theory. Now you see, this entire process consists of interaction of particles, particles uniting, giving rise to further particles. So this reminds us something which is called quantum field theory, and one man definitely comes into play. I know you have guessed it right. So in the next, so the question is that if we are dealing with our particles which are related to quantum field theory, what is the link between quantum field theory and string theory? Coming up next in the next part of our video. So quantum field theory, I would just like to show a quick visualization right on your screen. You see that these particles, the quarks, etc., all those point-like particles are being replaced with a one-dimensional diagram representing the path of a point particle by a two-dimensional surface representing the motion of a string. Now, whenever we talk about quantum field theory, one person comes into play. Yes, you're right, Richard P. Feynman. Now, once we are using quantum field theory, we see Feynman's diagram. Now, we can, extrapolate Feynman's diagram in order to create those strings. I'm going to say there is a relation between Feynman's diagram, which uses quantum field theory and interaction of particles, and finding something on string theory. Right on your screen, you see, I've just given a kind of a brief idea. So the vertex which is in the Feynman diagram actually represents a number which is proportional to the strength of the interaction. So you see in the screen, I have written that the line is indicative of a particle's progress, but not a trajectory. This is the solid line for particle, and here an electron enters, emits or absorbs, and wavy line of other type, a line for a particle which is its own antiparticle. So what I'm trying to see is that you saw the Feynman diagram, the vortex. Now coming up next, right on your screen you see that this is something which had got no vertex discontinuities. Now string theory actually, the vertex in Feynman diagram calculation represents a number which is proportional to the strength of the interaction. Now you see on the screen, the left hand side Feynman's diagram, there are no vertex discontinuities at all in the string theory. But Feynman diagram, you will see that there are vertex. So everywhere we see the same smooth evolution of the string surface. In string theory, there are no vertices, and hence string theory has very few parameters. So what I'm trying to make a point is that Feynman's diagrams, when they are extended further into string theory, you will see that these vertexes, they vanish. Just a normal kind of a discrete and continuous concept. Now when these vertexes are vanishing, what we get is a less number of parameters. So the prediction becomes easier, calculation and mathematics becomes easier. So just wanted to show you that actually from Feynman's diagram, if we discontinue with the discrete vertex which are there on the Feynman's diagram, then we can extrapolate and find out further and make it into string theory. So what I'm trying to make a point right on your screen is a quick summary. String theory rejects the idea of a point particle as the fundamental constituent of the theory, which is a central concept of quantum field theory. By introducing one-dimensional extended objects, give rise to a natural smallest scale in the form of string or length. So that is basically what I'm trying to mean, the relation between, or you can say difference also, between quantum field theory and string theory. Feynman's diagram vertices can be expanded to tube-like structures, and these are pretty continuous in measurements. So we all know that the fundamental forces of nature, which is quite common, that electromagnetism, then we have got strong force, weak force and gravity. Three of them has been united and finding a safe position and staying happily in the standard model of particle physics. But the problem creator is our dear Mr. Gravity. Now this gravity, as because every single force, I mean to say every single fundamental force has a carrier which are gluons and photons for in case of light, we are unable to find the carrier for gravity. Physicists have hypothesized this to be a graviton, but this graviton is also a fundamental search particle in string theory, which is part of quantum gravity. Now why this is so? Let us quickly have a look onto that. You see that in string theory we deal with two types of strings, open and closed strings. So the strings vibrate, twist and fold, they produce in many tiny dimensions. On large scales, strings look like ordinary particle. In large scales, because we are moving away, we are zooming out, so those strings will be very small and they will look like ordinary particles. Now the string theorist still now has make a kind of a hypothesis, or mathematically we are trying to find out that these vibrations will actually produce one vibration which is called a graviton. So plausibly, I would say reasonably, it is okay that we are trying to find out something which is called a graviton. So the standard model with the graviton, once it finds a place, it will all the problems of finding a unified field theory will be solved. So you see on the screen, I have given a kind of a brief description that there is an open and closed string, and these vibrations can be identified as graviton. Other gravitational modes, open strings exhibit the properties of photons and gluons. So you see that photons and gluons, which are already there in standard model, I mean to say which has classically been defined using quantum field theory or others, now these vibrations actually exhibits photons and gluons and possibly graviton in string theory. But here comes a very important thing. The string theory predicts that these gravitons or these vibrations are not taking place in one dimension. there are many dimensions in which you and me, we are living in. Isn't it fascinating? We are unable to see. We only see length, breadth and height, and maybe Einstein has given us that knowledge to think about time. But string theory says that there are 10, 11 and huge number of dimensions. What are those extra dimensions and why do string theory at all need those dimensions? Coming up in the next part of our video. In general, when we look into a Cartesian space, the general space that we are living in, then we find it is only the length, breadth and time. However, Einstein's four-dimensional space-time has now given us an understanding. But the problem is that, it would be very difficult without mathematics to explain why do we need those extra dimensions. I mean to say these are two mathematical calculations which I have to make a separate video. But right now let us understand the one reason is what is called a mathematical consistency. And I mean to say if we make those dimensions in which those strings really vibrate, then the mathematics becomes easy and we can find out those which we are trying to find out. Right on the screen, I have given a brief summary that why string theory needs additional dimensions for their mathematical consistency. Modeling space-time in different number of dimensions, a theory becomes more mathematically tractable and can perform calculations and is also used in describing phenomena in condensed matter physics. There are also situations where theories in 2 or 3 space-times are useful at describing phenomena in condensed matter physics. Finally, there exists a scenario in which there are actually more than 4-dimensional space which have nonetheless managed to escape detection. So, although it is too mathematical, I am trying to make an effort to let you know when we plug in those parameters from holographic principle, Poincare, all those things which is totally out of the scope of this video, we find that we need really extra dimensions so that the mathematical consistency is there, the mathematics becomes more tractable and we can really find out all that we are searching for, that is the grand unified theory with the search of graviton. However, there is one thing very easy to understand. Before I show you the illustration, let me tell you in general what we know of Einstein's general theory of relativity, that there is a matter, for example a mass, it can be a sphere or anything, it causes a dent and this dent causes a space-time curvature and we call this curvature as gravity. Simple, right? But what about that these strings are vibrating in a space-time and these vibrations require a lot of space. So if you put a sphere, if you put me, if you put any object, it won't require a space, right? I mean to say it has got length, breadth and height. It has got a specific space in which it occurs and you get the geodesics and you calculate what we call gravity. But what about those strings which require space? I mean to say you are in a small room and they are saying, hey, come on, give me a space. I really cannot move out. That is why we require additional dimensions. Right on your screen, you see I have given a kind of an analogy between space-time curvature, classical general relativity with the string theory. And you will see that 1, 2, 3, these electrons, once they are vibrating, they actually needs a lot of space. Now, this is again very, very wrong. I would say this is not the right approach to make you understand about dimensional analysis or why string theory. But you can say intuitively this is fine, that the strings move in space and these spaces require, these strings require a lot of space, a lot of extra area in which they can vibrate. And remember, only we have just discussed that only when they vibrate, then they will be able to produce those particles, gluons, subatomic interaction. Now, the question is that where are those dimensions? I mean to say we cannot see this in the room. I cannot see it in my study. You cannot see it over mobile, right? So the very basic question is that if there are at all dimensions which are 10, 11, which string theory predicts, then where are those dimensions? Let us find those hidden dimensions in the next part of our video. So the concept is that the entire dimension is being curled up in a tiny, tiny, tiny small space that we are unable to see. So this is a phenomena which is called compactification. We will come to that. Just let us have a look on your screen. compactification is one of the way modifying the number of dimensions in physical theory. It tries to reconcile the gap between the conception of our universe based in 4 observable dimensions with 10, 11 and 26. The extra dimensions are wrapped up themselves and curled up in what is called a Calabi-Yau manifolds or an orbifolds, and they are as small as 10 to the power minus 33 centimeter. Now there is a history, I'm not going into that, how these curled up dimensions started up, but just try to understand that these dimensions are not big. They are so small, they are curled up in a space that we are unable to see. To give you a visualization, right on your screen you see this is a cylinder, and pretend that this is a one-dimensional line, the world that we observe, and imagine a stretched sheet of rubber which lives on the cylinder, and going around this circle proxies a compact extra dimension from our point of view. So as you can see that this is something which is called compactification, and we find out that these extra dimensions which are required for the strings to vibrate, which are required for are basically something which we find in the curled up space. The person who first proposed this curled up dimension is Theodor Kaluza, and later being assisted by Oscar Klein. Right on your screen, I've just given an overall idea. Kaluza-Klein is a classical unified field theory of gravitation built around the idea of a 5th dimension beyond the common 4 dimension of space-time, and considered an important precursor of string theory. So you can imagine as a garden hose pipe, very long, and it has got a kind of circumference. When you're viewing from a very distant place, you find that hose pipe to be a single thread. That is the string which is vibrating around space, right? And that small circumference which is we are unable to see, that is the curled up space. Bosonic string theory told 26 dimensions. M theory says 11 dimensions. Some theory says 10 dimensions. These dimensions are vibrations required to produce interaction of particles, and they are very small and they are curled up. To give you a better visualization, right on your screen you can see that this is a kind of a cartoon where this ant is moving around, right? And these are the larger dimensions, and the compact dimensions are curled up. So Klein introduced the hypothesis of Klein's foundations, and later with this Sundaram Randan model, and further in string theory, we are in search of these dimensions. Why we cannot see? Because it is curled up. Just to summarize, look on your screen. Kaluza-Klein actually has a unification on 5 dimension. He proposed that the 5th dimension is very small, 10 to the power minus 35 centimeter. And this classical extension of 15 components of metric tensor has been found out. The 10 components identified by the 4D spacetime, 4 components with the electromagnetic vector, 1 component with an unidentified scalar which is called a radian. This is again a hypothetical particle radian. It is wonderful to see Kaluza-Klein's 5-dimensional general theory of relativity, how general theory of relativity he extended to 5 dimension. I'm very sure that I'm going to make a video on Kaluza-Klein's extension of field equations to 5 dimension with the mathematics in it. But this is what is called compactification, and that is why we cannot see the dimensions. And this is how Kaluza-Klein hypothesized the extra dimension, and he called that it is curled up in a small space, which is just like an analogy we use with a hose pipe and its circumference. So far so good. We are coming to the last part of our video where we further need to use those dimensions, because these dimensions that we require, these have been further extended into nice mathematical framework. What are those? Coming up in the next part of our video. So the concept of dimension has been further extended in what is called a brane. Mind the spelling, it is not B-R-A-I-N, it is B-R-A-N-E. So brane is basically a kind of a generalization of the notion of high dimension of particles. Right on your screen I have given what actually brane is. In string theory, a brane is a physical object that generalizes the notion of point particles. Brane is an object extended in one or more spatial dimension which arises for the proposal of unified theories of quantum mechanics and general relativity. There is a zero-dimensional brane, which is a point, one brane, one-dimensional string, two brane, two-dimensional string, p brane, nine-dimensional object, m5 magnetic charge, m2, and so on. So I would make a separate video, don't worry, on brane, because brane really requires the brain to make things work. It's a very advanced concept on string theory where these branes really are associated with the dimensions. So you see that just on an analogy, you can imagine that a point zero, or when we are formalizing the higher dimension for the strings to vibrate, these higher dimensions requires a mathematical framework to work on, and that is what is called a brane. And these branes moves around through which the particles vibrate, and these vibrations happens in different dimensions which we are unable to see. There is one very important brane which is called D brane, or the word D is taken from directly boundary condition. So let me tell you what happens actually before I show you the illustration. There are two types of string we know, open and closed. Now when it is an open-ended string, these strings keeps on vibrating, right? It is wiggling around here, around here. Now when it is wiggling around or it is moving around space, it needs 2 points to, I would say, to anchor itself, right? It needs 2 end points. These 2 end points where the strings, I mean, so open-ended strings will anchor and will find it out. That is what is called D brane. Now you see on your screen, so D brane arises with open strings as open strings travel through space-time, and its end point should satisfy either directly boundary condition or Neumann boundary condition. So boundary conditions, as you understand, when you are using it in partial derivative, it should formulate the boundary condition. That means it just cannot move around. Come on, we need a mathematical framework when these strings need to anchor and find itself in a position. So that is done through D brane, which actually satisfies and follows either directly boundary condition or the Neumann boundary condition. So you get the open-ended strings which are bound to certain areas which are called D branes. So far so good. So in this part of the video we have understood what is called different type of string theories, supergravity. We got type 1, type 2, all those string theories. Just have a look on the screen. So we got type 1, type 2, SO32, 11-dimensional supergravity, etc. But the question still rises that, is there any single theory? Because the entire quest for string theory is to find out one single theory. Is there any single string theory or a theory which actually encompasses or consolidates the entire type 1, type 2, string supergravity, supersymmetry, etc.? Let us find it out in the next part of our video. Well, the actual meaning of M theory, or the meaning of the word M, is not yet clear. Somebody says it can be membrane, it can be mystery or whatever. But however, we need to find out that this was actually formalized or hypothesized by Edward Witten. Right on your screen, you see I have given a basic idea. That idea of M theory is to bring the 5 versions of string theory together. So the triangle where you saw there is a big question mark is now being fulfilled. At the center lies the M theory, and all other type 1, type 2, E8, heterotoic theory, and 11-dimensional supergravity moves around. So you see each basic particle is created at the most fundamental level. That means it cannot be further subdivided by vibrating strings. M theory would need 11 dimension to unify string theory. Some of the extra dimensions can be thought of as curled up into spiral spaces. So that is what is M theory. Now M theory has got certain obviously limitations, because M theory has not yet been found out on a Large Hadron Collider, or even the mathematics is not yet very clear, right? So we are still in search of what is called M theory. However, M theory seems to be promising. The reason is that M theory unites all those theories together. Right on the screen is a brief summary. The theory combines 5 superstring theories and supergravity, unifies all consistent versions of superstring theory. It is first conjectured in 1995 by Edward Witten, and it ushered what is called a second superstring revolution. So there was a first superstring revolution and there is a second superstring revolution. Quickly on your screen, a brief summary of it. It attempts to create a theory of everything, aims to unify quantum mechanics with general relativity. According to Witten, as I told, M stands for magic, mystery, membrane. Investigations in M-theory leads to important theoretical results, linking M-theory to experiments and focus on compacting its extra dimension, and it naturally predicts what is called the existence of a graviton. I just wanted to mention you one thing, that graviton is, suppose if we find it out at all, then it should be a spin 2 kind of a particle, right? Because the stress energy tensor, which in Einstein's relativity predicts, shows the mass part of the field equation, is also a kind of a rank 2 tensor. So it has to be matched that way. So as all neo-theories would, and we are still searching to find out graviton or M-theory, which seems to be promising and can be found out in the near future. So that's all. That brings us to the end of our today's video. I won't take to summarize because it has been quite a long video, but as you understand, the string theory without the mathematical calculation seems very weird, seems very hypothetical, things are not quite okay, dimensions curled up, what are all those means? So I'm sure I am getting a lot of good comments from the subscribers requesting me or telling me that why don't I make a video on the basic mathematics of string theory. I will definitely would. So just to sum up, as you see that this is a theory which is still going on, lot of research scopes are there, lot of young too difficult. So string theory is basically promising us to find out these particles, the vibrations, the dimensions, in order to find out a theory of everything, and we don't have to look here and there, we don't have to look for any other, and the search of graviton, how the strings vibrate and why do we need these extra dimensions, why can't we see those dimensions because they are being curled up, and Kaluza-Klein's formalism into finding out something which is a 5-dimensional theory, and ultimately in search of M-theory, which was founded by Edward Witten, and we are still finding it out. Definitely physics and mathematics, the way it has advanced in last 50 or 100 years, shows us that we will be able to find out, but we have to wait. There are a lot of researches, a lot of mathematics, a lot of cracking of the head is going on, so that we can really find out the string theory, and hopefully one day Einstein's dream of unifying quantum mechanics. The Christmas is coming, and before that I want to wish you all a very happy Christmas and season's greetings. Wherever you are, in which part of the world you are, please stay happy, spread the message of love and happiness amongst everybody, because Christmas is the time when people and around the world we all feel happy. Please put up your comment, click on the like button and click on the notification bell and click on all, so that get you all the notification from Physics for Students. This is Shaunak signing off from Physics for Students, promising you to come back very soon with yet another video. Till then, goodbye.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.